Hey, Flipped Chemistry, how you doing? We're jumping into our next big idea. I'm not Sid the Science Kid, but that just totally came into my head. Big idea. Anyway, we're getting into organic chemistry. Now, when I was taking chemistry in college, we had to take 1 year of regular inorganic chem, and then we took a year of organic chemistry. And organic chemistry had the reputation of eating people. It was this big, terrifying, horrible thing. But when I took it, honestly, it was much easier for me than inorganic chem, than the chem that we've been doing so far. You only get 1 chapter of organic chemistry in high school. If you major in the sciences, you'll wind up with a whole year of it. And let me tell you, this was my favorite part of chemistry. I loved chemistry. I loved organic chemistry because it's more about 3-dimensional objects and shapes and manipulating things in your mind as far as like trying to picture something a certain way. And geometry is the same way. I love geometry. It's my favorite math. If you like geometry better than you like algebra, you will like organic chemistry better than you like regular chemistry. If you hated geometry, then I'm sorry, you got to do it. So, clench and bear it and we'll get it done. But organic chemistry is really nothing that you need to be afraid of. It's going to be great. Let's jump right into it. Organic chemistry is the study of covalently bonded carbon. Every molecule that you're going to look at in this chapter is based on carbons covalently bound to other carbons. Sometimes they're very, very, very big molecules. Sometimes they're smaller. In the real world, they tend to be monsters, but in class, we let you use some small ones to help you understand the ideas. We call these molecules hydrocarbons as well because they're mostly made up of hydrogen and carbon. So hydrocarbons. Carbon, because it can form 4 bonds with other atoms, it tends to form very stable, large lattice kind of molecules. And those long chains of carbons serve as the backbone for all the chemistry of life. Principal elements involved are carbon, nitrogen, oxygen, hydrogen, and halides. Anything from that fluorine column, group 7 of the periodic table. So some things that we need to keep track of. Carbon can always form 4 bonds. Nitrogen can always form 3 bonds. Oxygen can always form 2 bonds. Hydrogen or halides can form 1 bond. And so when you are drawing molecules and you're looking at the shapes of molecules, the atom is going to dictate how many bonds come out of that. And you will become very familiar with that as we go on here. The main way to express the arrangement of an organic molecule is with something called a structural formula. And my picture is hovering over one. There you go. This is a structural formula. And it shows you not just 3 carbons and 5, 6 hydrogens and a chlorine and a bromine, but actually how it's arranged, because you could take those elements and arrange them in multiple ways, and you would get different sorts of chemistry, different sorts of properties out of those elements if you arrange them differently. So we use structural formulas that are actually pictures as opposed to just C3H whatever. Okay. If you have 2 molecules that have the same empirical formula, the same letters and numbers, but have different structure, then we call those 2 things structural isomers. Like an isotope is an atom that has a different mass but the same number of protons. An isomer is a molecule that has the same atoms in it, but they're arranged differently. And then when we start to draw these things, there's so much hydrogen. We oftentimes omit hydrogen from our drawings, and we'll just let you assume that every bond that isn't specifically labeled as going to something else goes to hydrogen. And then oftentimes we will also omit drawing all the little letter C's for carbons, because there are so many carbons that we'll just draw intersections of lines and we'll say every node is a carbon unless I've told you differently. Let me show you some examples of structural formulas. This is the one that was up in the top corner of the last slide. And here we have 3 carbons, and each carbon has 4 bonds, right? 1, 2, 3, 4. 2 of them go to hydrogens. This one goes to a chlorine. This one goes to the next carbon. 4 bonds again, a hydrogen, a bromine, and 2 carbons. Another carbon, 4 bonds again, all 3 of them to hydrogens except for this carbon. So carbon always has 4 bonds. Hydrogen or halides like bromine and chlorine always have 1 bond. This is another example of a structural formula, and here we've simplified things a little bit. We've just said H3C, and I haven't drawn like bond, bond, bond. Same thing, CH3, I haven't drawn bond, 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 because I want to simplify this and streamline this. And if I just tell you that there's 3 hydrogens attached to this carbon, then you can picture that in your mind. I also didn't bother telling you that this was a single bond between carbon and oxygen. You can figure that out. But the sulfur is interesting here. The sulfur has a double bond to this oxygen and single bonds to these other ones. So we need to call that out. So we're going to draw it that way, right? If I had just said H3COSOCH3 and then I'd done a double bond up to this oxygen, you wouldn't be quite sure where all those bonds went. So this is an example of drawing fewer bonds to help things be clear. This is an example of drawing no hydrogens that aren't part of a functional group and labeling no carbons. So all of these intersections are carbons. This is a carbon, 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 carbon. But where they haven't told you anything different, we get to assume that it's a carbon, right? So this has 6, 7 carbons in it, but none of them get a C in the drawing because we can figure that out. Almost everything's a carbon. And then if you look at these carbons that are here, there should be another bond coming out here because 1, 2, 3 bonds. Carbon always has 4 bonds. 1, 2, 3. 1, 2, 3. Where's the 4th bond? Well, there's another bond coming out of each of these going to hydrogen, and they don't bother drawing it because they want it to be simple. And just like you can assume that every node that isn't labeled as something else is carbon, you know that carbon has to have 4 bonds. So if I've only drawn 3, then you know that there has to be a 4th one going out to a hydrogen. Okay, so they're letting you assume a lot in this so that it gets smoother and simpler to see. That structure that had the 6 carbons in a ring, the ring was drawn with alternating double bonds, and that is true. But what's interesting about a 6-carbon ring with alternating double bonds is that this double bond can all of a sudden pop over here and make this one go over here and make this one go over here. So the electrons can actually kind of orbit through this, and we call this a delocalized electron sort of situation. And so the delocalized electrons in bonds, the electrons can spread out throughout that ring. And you actually get a situation where all of these bonds are kind of like 1.5 bonds. And so they draw something like this or something like this to help you see that the electrons are not just hard locked into this with a single bond and a double bond and a single bond and a double bond, but the electrons are actually able to float around that molecule a little bit. So one of these 2 symbols will help you understand that this second bond is shared throughout all the members of that ring. 2 kinds of organic molecules. Aliphatics, which are straight chain or branched chains or even loops, as long as the loop is not that thing I just showed you. And then aromatics. Aromatics are ring shapes where the valence electrons are delocalized and can float around the ring. So the structure I just showed you a moment ago is an aromatic, and everything else I've shown you so far is an aliphatic. Aliphatic has straight chains or branched chains or a ring, but not that sharing electron kind of ring. Okay. And then an alkane. This is a group of hydrocarbons where there are no double bonds. Every bond is a single bond. And an alkane is going to be the majority of things that you deal with, honestly. In organic chemistry is going to be an alkane, at least in high school. Most of the time, we call these saturated hydrocarbons because they've been saturated with hydrogen. There's as many hydrogens stuck to that carbon chain as there could be. Think about it. If you had a carbon with 2 hydrogens and a carbon with 2 hydrogens, and that chain keeps going. If those 2 carbons all of a sudden become a double bond, now they've got 1, 2, 3 bonds for each carbon, and they can each only have 1 hydrogen sticking up, not a second hydrogen. So that's why we call a alkane saturated. It has all the hydrogen it can have, and it tends to be more stable, less reactive, and they're harder for your body to know what to do with, which is why saturated fats tend to sit around inside you and just keep making you fatter. An ethane molecule, you see the word ane here? That's from alkane. That means that it's all single bonds. Eth has to do with there being 2, and we'll get to that specifically in a minute. But this is 2 carbons that have a single bond, ethane. Prop means 3 carbons. Ane, again, is because it's an alkane. They're all single bonds. Propane, 3 carbons, single bonds, propane. Okay? An alkene is a chain of carbons that has at least 1 double bond somewhere. And so we don't call it an alkane. If there's at least 1 double bond, we call it an alkene. And an alkyne, similarly, would have at least 1 triple bond. Now, there are molecules that have double and triple bonds, and so which category they fall into is a little bit confusing. But for right now, just alkane, no double bonds. Alkene, at least 1 double bond. Alkyne, at least 1 triple bond. Okay, and they become more reactive as you make more complicated bonds. A double bond is a more reactive thing than a triple bond. I'm sorry, than a single bond, and a triple bond is more reactive still. And so these would be unsaturated because they don't have as much hydrogen as they could possibly have. Some hydrogen was kicked off when that double bond or triple bond was formed. Okay, alkenes, alkynes. Here's a picture. This is ethene, 2 carbons, eth-ene, because double bond. Propene, prop, 3 carbons, ene, at least 1 double bond. There it is, 3 carbons with a double bond. Bute is 4, ene, because there's at least 1 double bond. Butene, there it is, 4 carbons with a double bond. Okay, double bonds, just as a reminder, we talked about this a while ago. Double bonds are a shared sigma bond, a shared end-to-end orbital, and then a shared pi bond, electrons overlapping above and below. Triple bonds, alkynes. This would be propyne, 3 carbons with a triple bond. Okay, there's another way of drawing that. 3 carbons with a triple bond, propyne. And just again as a reminder, a triple bond, the overlapping sigma bonds, and then above and below 1 pi bond, and left and right another pi bond. So it winds up looking kind of like this, a barrel of electrons that are being shared between the 2 atoms. Now, we name organic compounds, as you've already seen, with a, we count the longest chain of carbons that there are, and sometimes you got to turn a corner from the way that it's drawn to get the longest chain, but you get the longest chain, and you use a Greek prefix to tell you how many carbons there are. And as you've already seen, meth is 1, eth is 2, prop is 3, bute is 4. The list keeps going. Look at table 18-2 in your book. Okay. And then the suffix of that word is given by the bonding categories, an alkane, an alkene, or an alkyne. So let's do a couple of these together. 4 carbons, if you look at the table, 4 is bute, and all single bonds, so that's butane. Don't worry about this guy yet. Okay, we'll deal with him next time. Okay, here we have 1, 2, 3, 4, 5, 6, 7 protons. Sorry, 7 protons, 7 atoms. And 7 is hept, and this is all single bonds. So this would be heptane. Good job. And here we have 1, 2, 3, 4, 5. If you look at your table, 5 is prop. Sorry, 5 is pent. And so don't worry about these guys yet. 5 is pent, all single bonds. This would be pentane. Alrighty. So we're going to do a whole bunch more examples in class. If this doesn't come clear yet, it will very soon. Let me know if you have any questions in the comments field below, and I'll get to them as quickly as I can. And otherwise, I'll see you in class tomorrow. God bless you. Jesus loves you, and so do I.